Hello and welcome to another Ladybird book. This one, How It Works, the Aeroplane. Let's have a look at the back cover, and we see that in the time that this was produced by Wills and Hepworth in England, there were 3 titles in 654: the motor car, the rocket and the aeroplane. So let's have a look at this, book 3 in series 654, the aeroplane. If you throw a ball into the air, it comes down again at once. Why doesn't an aeroplane fall to the ground? How does such a heavy machine get up there in the first place? What's the difference between a piston engine and a jet engine? How does a helicopter hover? Why does an aeroplane have a ceiling? What are sonic bangs? The answer to these and many other questions will be found in this well-illustrated and easily understood Ladybird book about how an aeroplane works. 2 shillings and 6pence. First published 1967. How It Works, the Aeroplane. Introduction. Of the 3 modes of travel, by land, water or air travel has always presented the greatest problem. It is only in fairly recent years that man has been able to build a reliable machine to transport him efficiently and safely in the air. That machine is, of course, the aeroplane, and it is the purpose of this book to describe as simply as possible how and why an aeroplane works. Motor cars travel along solid ground and have only to be propelled. Boats and ships are supported by the water and will remain afloat under all normal conditions. But an aeroplane is heavier than the air in which it has to fly. Yet it must be got off the ground, made to stay in the air in spite of its weight, and finally brought back to earth gently without damage. To discover how an aeroplane works, we must first find out about the air itself, how it behaves and how it affects an object moving through it. The way an aeroplane is built to make use of the air is important, as is also the method by which it is controlled and made to obey the wishes of the pilot. It's a big subject, but truly a fascinating one. The air. There is a huge envelope of air around the surface of the earth. This air has an atmospheric pressure due to the weight of all the air above it. As we leave the Earth's surface and go higher, the pressure becomes less because there is less air to press down. At sea level, the air pressure is nearly 15 pounds on every square inch of surface. At 20,000 feet, this reduces to 7 pounds to the square inch. At 60,000 feet, the air pressure is only 1 pound per square inch. Air is also compressible, which means that it is more compressed or denser nearer the ground. Once again, this is because of the pressure of all the air above. Because it is more dense, air at sea level is heavier than the air higher up. If we use the same height examples as before, we find that 100 cubic feet of air weighs nearly 8 pounds at sea level, only 4 pounds at 20,000 feet, and less than 3/4 of a pound at 60,000 feet. These differences of air pressure and density have a very great bearing on the design of aeroplanes, a fact that you'll be able to understand better as you read further into this book. Lift and drag. To enable an aeroplane to fly in the air, it must be given a lifting force at least equal to its own weight. How is this lift to be provided? Let's first consider a more simple flying object, a kite. The strings of a kite are so fitted that when the kite is flown, it is not flat or upright, but inclined at an angle, the front or the leading edge being higher than the rear or the trailing edge. Have you ever noticed this? The angle at which the kite is inclined is known as the angle of attack. As you give the kite speed by holding the string and running, it will rise into the air, and if you pay out the string, it will rise higher and higher. The upward force which makes the kite rise is called the lift. If you grip the string tightly and draw the kite towards you in the air, you'll feel a pull as the air tries to hold it back. This is known as drag, and it acts against the direction of flight. With aeroplanes, lift is a useful force which is essential to flight. It's obtained partly by the wings and partly by the aeroplane's forward speed. Drag is a backward pull which hinders forward motion and has to be reduced to a minimum. Aeroplane wings. So far we've been dealing with the simplest form of wing, the kite, with its flat surfaces and light weight. Aeroplanes need something much more efficient, and designers have developed wings of special curved shape known as aerofoils. An aerofoil is really made up of two surfaces, an upper and a lower, each with a different curve or camber. There are two main reasons for this. Firstly, a curved surface gives better lift, and secondly, an aeroplane has to get a heavy machine off the ground, so it must have thickness into which the necessary strength can be built. In the previous chapter, we mentioned the angle at which the kite was inclined upward. That is the angle of attack. Aeroplane wings also have an angle of attack and are fitted to the fuselage with the leading edge slightly higher than the trailing edge when seen in the flying position. An increased angle of attack gives more lift, as with the kite, but also increases the drag. For normal flight, the angle of attack has to be just right to ensure sufficient lift and at the same time cause as little drag as possible. On modern, fast-flying aeroplanes, the angle of attack is very small, usually not much more than about 2 degrees from the horizontal when in level flight. The angle of attack is the angle between the relative airflow and the chord line. The chord line is the line joining the centers of curvature of the leading and trailing edges. Airflow over an aeroplane's wing. For an aeroplane's wing to give the lift required for flight, the general airflow over and around the wing must be streamlined and not turbulent. The amount of lift the wings give will depend on 1. Their shape, 2. Their area, 3. The density of air through which they fly, 4. The speed at which the air passes over them, 5. The angle of attack. Numbers 4 and 5 are the ones which can be controlled by the pilot, although he has some control over number 3 by choosing the height at which he flies. For a given speed, the amount of lift is controlled by the angle of attack. The greater the angle of attack, the greater the lift. This is true up to the angle of attack known as the stalling angle, when the general airflow becomes turbulent and there is a sudden decrease in the amount of lift. As the weight of a plane in the air is constant, the lift required to keep it flying straight and level must also be constant. Because of this, a test pilot can, at a safe height, fly straight and level, gradually reducing his speed but increasing his angle of attack so that the lift remains constant until the stalling angle is reached. In straight and level flight, the stalling angle will always be reached at the same indicated airspeed, which is known as the stalling speed. Forces acting on an aeroplane. We can now sum up the various forces which act on an aeroplane and see how they affect the whole machine in straight and level flight. An aeroplane gains almost all of its lift from the wings. The remaining parts help very little. On the other hand, it is the body or fuselage, engine mountings, and other protruding portions which cause most of the drag. We must therefore have all of these parts as smooth and streamlined as possible. A dart will fly better than a ball because it creates less drag. So this is the sort of shape aircraft designers must try to achieve. Lift on an aeroplane acts vertically upward. The machine's weight pushes vertically downward. To fly straight and level, the lift must equal the weight. If the lift were greater, the aeroplane would go higher and higher. If the weight were greater, the machine would get lower and lower until it hit the ground. Then there are the horizontal forces, drag, which as we know is a backward force holding the aeroplane back, and thrust, which is the forward pull provided by the engines. Just as lift and weight are equal for straight and level flight, so the thrust must also equal the total drag. So long as thrust is greater than drag, the aeroplane will increase its speed. Stability and movements of an aeroplane. Another matter which greatly concerns designers of aeroplanes is stability. This can be described briefly as the way an aeroplane itself corrects unwanted movements caused by air disturbances without the pilot having to adjust his controls. There are three kinds of movement which the aeroplane's natural stability is designed to correct. 1. Pitching. This is a movement in which the nose of the aeroplane is forced up or down by some disturbance of the air. An aeroplane must have longitudinal stability to bring the nose back to its original level position. The tailplane is the part fitted to do this. Rolling. An aeroplane rolls when the wingtips are forced up or down. In this movement, the machine is likely to side-slip in the direction of the lower wingtip unless it is corrected by the lateral stability. Lateral stability is usually obtained by inclining the wings slightly upward from the fuselage to wingtip when the aeroplane is made. The angle at which the wings are set is known as the dihedral angle and is not adjustable. Yawing. Point 3. This is a turning movement in which the nose tends to turn left or right and the aeroplane tries to fly sideways. The tail fin is fitted to provide directional stability and keep the aeroplane in its proper straight ahead position. Controlling the aeroplane. However stable an aeroplane may be, the pilot must be able to control it, to increase or decrease height, and to change direction whenever necessary. Longitudinal control raises or lowers the nose of the aeroplane and is provided by elevators at the rear of the tailplane. Forward movement of the pilot's control column lowers the elevators. This increases the upward force on the tail, causes the nose to tilt downwards and the aeroplane to descend. The operation is reversed to raise the nose and climb. Lateral control is obtained by the pilot moving the control column sideways or by turning a half wheel at the top of the column. This operates ailerons at the rear of each wing near the tip. Movement of the column to the right lowers the left-hand aileron, increases the lift on the left-hand wing, and banks the aeroplane to the right. At the same time, the right-hand aileron has been raised to reduce the lift on the right-hand wing and so lower the right-hand wing. In this picture, this is shown looking at the tail of the aeroplane. Directional control. This is effected by means of a rudder on the tail fin worked by the pilot's feet. Pressing the left pedal down turns the rudder to the left and increases the force on the left of the tail fin and pushes the aeroplane's nose to the left. More about stability, the automatic pilot. The feature of stability was dealt with on page 16, but it is an important subject and worth enlarging upon. Stability varies for different kinds of aeroplanes. Fast fighter aircraft must be able to maneuver quickly onto an enemy plane or ground target. They are in the air for fairly short periods. For these reasons, they have less built-in stability than larger machines and more direct pilot control. It would be a very poor fighter aircraft which automatically went back to its original position every time a pilot tried to maneuver it. On the other hand, large airliners which fly steadily from one point to another for several hours at a time need a greater degree of built-in stability so that the pilot does not have to keep adjusting his controls for every little movement of the aeroplane. This would be very tiring. For instance, on a flight across the Atlantic. To help the pilot still further and give even greater stability, most commercial aeroplanes are fitted with an automatic pilot, sometimes known as George. This is a system of gyroscopes and electronic devices which keeps the flying controls in the right positions for straight and level. The pilot can switch to George when he wishes to rest or move about the aircraft. Airspeed and ground speed. There is another aspect of flying we must now know about, that is flying speeds. There are in fact two kinds of speed: the ground speed, which is the actual speed of the aeroplane in relation to the ground, and the airspeed, which is the speed relative to the air. These are two quite different things. Let us go back to the kite for a moment. If in still air you run with the kite at 5 miles per hour, its ground speed will be 5 miles per hour, because that is the actual speed at which you are pulling it over the ground. Now, suppose you're running at 5 miles per hour against a light breeze of 5 miles per hour. The ground speed will still be the same, but because the air is passing the kite at 10 miles per hour, the airspeed of the kite will be 10 miles per hour. That is the speed at which you are running plus the speed of the air blowing past the kite. Stand still with your kite in the same breeze. Its ground speed is now nothing, but the air is passing the kite at 5 miles per hour, so its airspeed is 5 miles per hour. Ground speed decides how long an aeroplane will take to fly from one place to another. Airspeed provides the lifting force and the drag. Your kite will remain in the air in a good breeze even if you stand still, and you will still feel the drag on the spring. Taking off. In the previous chapters, we've learned something about the air, how it affects an aeroplane, and how the aeroplane can be controlled. These have been very important chapters because they concern the basic principles of flight. Now it is time to see how an aeroplane actually gets into the air. First of all, the aircraft must be correctly positioned on the airfield, so it is driven along the ground under the power of its engines. This is called taxiing. When it reaches the end of the runway, it is turned into the wind, that is, toward the direction from which the wind is blowing. With the wind blowing towards it, the aeroplane already has a little airspeed. The throttles are opened, the engines roar, and the aeroplane rapidly gains speed along the runway. As the ground speed increases, so does the airspeed until the flying speed is reached. At that moment, the aeroplane can leave the ground and become airborne if the pilot slightly increases the angle of attack. The upward force of the air acting on the wings and the aeroplane's speed have provided the necessary lift to start it flying. After safety speed has been reached, the pilot can then ease back the control column to lift the nose of the machine further and so increase the rate of climb. Level flight and the speed range. For straight and level flight, lift must always equal weight. Lift is controlled by the angle of attack and by speed. If the pilot of an aeroplane increases his speed and does not alter his angle of attack, see those pages 12 and 13, the aeroplane will rise. Therefore, to maintain level flight, he must push the control column forward to lower the nose and so decrease the angle of attack. This restores the lift-weight balance. On the other hand, if the pilot reduces speed without altering his angle of attack, he will lose height. He must therefore pull the control column back and increase the angle of attack to keep his aeroplane in level flight. The pilot of an aeroplane may wish to fly as fast as possible. He may wish to fly at the most economic cruising speed to conserve fuel, or he may wish to fly as slowly as possible at the instant of landing. Aeroplanes are designed to fly at certain speeds and at certain heights. There is a maximum speed beyond which the power of the engines will not take them. There is also a minimum flying speed below which an aeroplane will not leave the ground. If it is already in the air, it will stall and crash. This is because the speed is too low to maintain sufficient lift even when the angle of attack is greatly increased. This is known as the stalling speed. How a climbing plane reaches its ceiling. On the previous page, it was shown that for straight and level flight, lift must always equal weight. If the lift is greater, then the aeroplane will rise. It follows that an aeroplane can climb if it has the power to provide more speed, and so more lift, than that required for straight and level flight. In theory, all the pilot has to do is increase speed or lift the machine's nose to increase the angle of attack, or both. In practice, it's not so easy because of the properties of air, which were mentioned at the beginning of the book. As the aeroplane climbs higher, the density of the air becomes less. This means less lift at a given true airspeed, which means that more power is needed to increase the true airspeed if the angle of attack is to remain the same. If the angle of attack is increased, more power is needed to overcome the extra drag. The higher an aeroplane flies, the worse is this effect. Unfortunately, with piston-engined aircraft, the less dense air also has an effect on the engine, so that even if the engine is supercharged, the power available also decreases with height. When all the power available is only maintaining straight and level flight at the best angle of attack, the aircraft is at its ceiling. With jet engines, however, the less dense air does not have such a serious effect on the power available. Turning. If you have ever flown in an aeroplane or watched from the ground, you will have noticed that whenever a turn is made, it is done in a slanting position, one wingtip lower than the other. This is known as banking. An object moving in a straight line tries to continue on that line when it is turned. A car being driven round a bend on a level road will only go round the bend so long as the tyres maintain their grip on the road. If it is driven too fast, the car will skid towards its original line of travel due to a force acting away from the centre of the turn. This is known as the centrifugal force. If the bend in the road is built up on the outside to form a sloping bank, the car will go round more easily and at a higher speed because the weight and centrifugal force combined will then act at right angles to the slope. If a pilot tries to turn his aeroplane without banking, it will tend to move sideways in its original line of flight, like the car in a skid. When banked and turned by the combined use of rudder, ailerons, and elevators, the wings provide extra lift against the outward force and allow the aeroplane to turn smoothly in the required direction. This is because all the forces are acting on the aeroplane and they are in balance. A nice glass of water. Landing. Landing an aeroplane, that is, transferring it from the air to the ground as gently as possible, is perhaps the most difficult manoeuvre of flying. It demands flying the aeroplane as slowly as possible without stalling, which in itself requires considerable skill on the part of the pilot. When approaching the ground, an aeroplane has both forward and downward speed. The forward speed, in relation to the ground, which has been progressively decreased by cutting the engine power, is still further reduced by landing into the wind whenever possible, but runway positions on modern airports do not always allow this to be done exactly, and crosswind landings sometimes take place. At a point close to the ground, forward speed in relation to the air is reduced by completely closing the throttle. As the speed falls off because the pilot has stopped all thrust but cannot reduce the drag, lift is maintained by raising the aircraft's nose slightly and progressively, thus increasing the angle of attack, and so keeping lift equal to the weight as the speed falls to its minimum for flying. Finally, as the forward speed continues to fall, a condition is reached when the aeroplane is no longer moving at its flying speed Ideally, this occurs at the moment when the wheels of the undercarriage touch the runway and the weight of the aeroplane is transferred smoothly from the air to the ground. Reduction of landing speeds. Landing speeds should be kept as low as possible, yet the aeroplane must be capable of a good turn of speed for normal flight. It's important that the lift of the wings equals the weight of the machine until the moment of landing. Because the landing speed needs to be kept down to a minimum, extra lift is required from the wings. How can this be obtained? By a greater angle of attack? The pilot can provide this by lifting the nose, but it is a relatively small movement, otherwise the aeroplane might stall. By more camber on the wings, by greater wing area. Both of these would help a great deal, but bigger wings with more camber create more drag and would slow down the aeroplane during normal flight. Aeroplane designers have found a means of overcoming this problem by the use of flaps. These are usually hinged at the trailing edge of the wings. During the landing operation, the pilot moves a control which causes the flaps to move out from the wings in a downward direction. This, in effect, especially in the case of the extension flap, forms a curved extension of the wings to increase their camber and area and provide enough extra lift to lower the stalling speed appreciably. During normal flights, the flaps are tucked up into the wings and flying speeds are not affected. The propeller. In piston-engined and propeller turbine aeroplanes, the propeller is used to provide the thrust which gives the plane its forward speed, which in turn gives the lift to make it fly. The blades of a propeller are not flat, but curved like an aerofoil and behave like an aerofoil. They are also set at an angle to the direction of rotation. As the propeller rotates, the blades strike the air at an angle of attack and develop thrust in just the same way that a wing develops lift. Imagine turning a nut on the thread of a bolt. For each complete turn, the nut is carried forward along the bolt. Similarly, the pitch or angle of a propeller's blades decides the distance the propeller moves forward through the air in one revolution. The faster an aeroplane is designed to fly, the coarser the pitch so that the propeller goes forward the greatest possible distance during each revolution. Modern commercial aeroplanes are usually fitted with variable and reversible pitch propellers, and the pitch angle can be varied by the pilot to suit flying conditions. A fine pitch, smaller angle, is required for takeoff to give maximum thrust at low forward speeds and high revolutions, and a coarse pitch, larger angle, to maintain thrust at high speeds and reduced engine revolutions when cruising. Reverse pitch completely reverses the action of the propeller so that instead of pulling the aircraft forward, it pushes it back. This is useful after landing to slow down the aircraft quickly. Piston engines. In a book of this kind, it's not possible to discuss in detail how the different types of engines work. All that can be done is to indicate the various engines in use and what are their basic differences. Piston engines operate on the same principle as those in an ordinary motor car. That is to say, they run on petrol and have pistons which move up and down in cylinders. These rotate a crankshaft which provides the drive. In the case of an aeroplane, the part being driven is the propeller. There are two main types of piston engine. One has the pistons and cylinders arranged in line as in the normal motor car. However, as the power is increased and more cylinders are used, this basic arrangement is varied. The cylinders can then be mounted in blocks in the shape of a V, an X, or an H. The second type is the radial engine, in which the cylinders radiate outwards from the centre and have a circular appearance when viewed from the front. When piston engines are used for aircraft propulsion, it is the radial type that is fitted on most multi-engined commercial aeroplanes. Inline engines are more common on smaller single-engine machines. Jets and propeller turbines. For all practical purposes, new commercial aeroplanes are designed for use with gas turbine or jet engines. The piston-operated petrol engine is no longer efficient enough for modern applications and is being gradually replaced. What then are the advantages of the aircraft gas turbine over its piston counterpart? It's more reliable and runs longer between overhauls. It produces continuous power instead of the typical beat of the piston engine. Its fuel, kerosene, is cheaper than petrol. It's lighter, better shaped to minimize drag, and free from vibration. Briefly, the operation of a turbine engine is as follows. Air is sucked into the front of the engine by a rotating compressor, then forced into combustion chambers into which the kerosene is sprayed and burnt. The tremendous heat thus generated expands the main volume of air, which moves at great speed through flame tubes onto the blades of the turbine wheel. This causes the wheel to rotate, and so the power is produced, and by a system of gears, this turns the propeller. In the case of a turbojet engine, the heated air comes out of the exhaust tailpipe as a jet which forces the surrounding air backwards and so pushes the aeroplane forward. Similarly, with a ramjet engine, the thrust is obtained purely by the jet. This type of engine is rarely used as it cannot work at low speeds because it relies only on forward speed, not a compressor, to force in the air. Flight instruments. Although the working of an aeroplane depends to a large extent on the properties of the air in which it flies, and on the design of the aeroplane to make use of these properties, the pilot has great responsibility in actually flying the machine. The flight deck of an airliner is an awesome sight to a novice, with all its instruments, dials, controls, switches, and indicator lights, which tell the pilot every detail of what is happening in every part of the aeroplane. There are so many of them that we can only mention a few. There is an airspeed indicator. This is connected to the tube you can sometimes see protruding forward from the nose or wing of an aeroplane. An altimeter gives the altitude or height above ground. A compass indicates direction and enables a course to be set. An artificial horizon shows whether the aeroplane is flying level without pitch or roll. This is most important for blind flying at night or in cloud when the pilot cannot see the ground. A turn and slip side indicator shows the pilot that he has the right amount of rudder and aileron movement and his rate of turn. That was the turn and side slip indicator. A rate of climb indicator shows the rate of ascent and descent. And there are a great many other instruments, as you can see in the picture opposite. Let's just turn the book for a moment so that we can actually have a look at and get a sense of all the dials and indicators that you can see here on the dashboard or the instrument panel of this larger commercial aircraft. Navigation. To get an aeroplane into the air and fly it is one problem. To fly it in the right direction and land at a point hundreds, perhaps thousands of miles away presents another set of problems altogether. The process of finding the way from one place to another is known as navigation, and so far as aeroplanes are concerned, this frequently has to be done at night or in cloudy weather when the ground cannot be seen. The basic aircraft instruments used for navigation, namely the airspeed indicator, the magnetic compass, and an accurate clock, only give information about what the aircraft is doing in relation to the air through which it is flying. But unless the day is windless, the air as a whole is itself moving in relation to the ground, so the navigator must calculate what allowances be made for the action of the wind on his plane at the height at which he is flying. Modern airliners have other navigational aids, Radar allows a pilot to see through the darkness or clouds, and radio direction finding equipment can be tuned in to ground stations so that the aeroplane's position can be accurately pinpointed. Of course, on a clear day when the ground is visible, navigation becomes a fairly simple matter of locating landmarks such as towns and rivers, which can be easily recognized. Auxiliary equipment. Modern airplanes are very complicated machines carrying a mass of equipment, all of which must work properly. Perhaps the most obvious item of auxiliary equipment is the undercarriage, which carries the wheels. The undercarriage is very useful on the ground, but as soon as the airplane is in the air, it becomes a nuisance. Hanging below the aircraft, it would get in the way of the airflow, cause drag, and reduce both lift and speed. That is why the undercarriage is always retracted into the wings as soon as the wheels leave the ground. Watch for yourself next time you see an aeroplane take off. The retracting machinery is controlled by the pilot and acts electrically or hydraulically. On larger aeroplanes, the flying controls are also power operated. The pilot's hands or feet moving the control column or rudder bar set a hydraulic system in motion, which in turn moves the ailerons, elevators, or rudder. To have to do this without power assistance would be very hard work, if it were possible at all. Electricity is needed to operate the lights and to work the radar and radio systems. Power for all this and other equipment is often provided by the main engines, but on some large aeroplanes, small auxiliary engines are fitted to deal with the extra power loads. The sound barrier. This chapter does not really explain how an aeroplane works. If you have been reading carefully so far, you will already know more about that subject than most people. Many aeroplanes, especially military ones, can now fly at the speed of sound and faster, so a little information on what this means is of special interest. When an aeroplane flies at speeds below the speed of sound, pressures caused by its movement through the air are transmitted to the surrounding air in the form of waves. These pressure waves travel at the same speed that sound travels in the air, that is about 760 miles per hour. Below the speed of sound, an aeroplane will travel behind the pressure waves and sound waves, and you can hear it coming. At exactly the speed of sound, it travels with the waves and the sound, and you will not hear it until it passes immediately above you. If it travels toward you faster than the speed of sound, it flies through the pressure waves, passes you before they do, and you will hear it coming after it has gone. Passing through the sound waves is often known as passing through the sound barrier. Sonic bangs are the shock waves caused by an aeroplane flying faster than sound, reaching the ears of someone on the ground. The helicopter. A book of this nature would not be quite complete without mentioning briefly the operation of an entirely different type of aircraft, the helicopter. It is used for all purposes where proper landing fields are not available, and it is often in the news carrying out difficult acts of rescue, transporting troops and supplies, even plucking astronauts from the sea. Vertical lift is provided by rotating wings or blades of aerofoil shape on top of the aircraft. The blades are set at an angle and provide upward thrust in the same way that a normal aeroplane propeller provides forward thrust. By forcing air downward, they lift the helicopter upward. The faster the speed of rotation, the greater the lift. Once the machine has gained height, the whole rotor system is tilted slightly forward. At this angle, there is combined upward and forward thrust. This gives the helicopter its forward speed as well as sufficient lift to maintain height. The little propeller which spins round at the side of the tail is to prevent the helicopter from rotating in the opposite direction to the rotor and acts as a rudder. Hovering over one spot is done by selecting the correct speed and setting of the rotor blades so that their vertical lift is exactly equal to the weight of the machine. And that is the whole book that we've just finished reading, all about the aeroplane and how it works, from series 654. I hope you've enjoyed that. It's been a technical read with lots of illustrations, and of course you can always go back to the video, read or hear me read aloud a section or read it on your screen along with me, and then pause your screen or your device to look at the illustrations which have been quite detailed but completely support the text that we've looked at together. How it works, the aeroplane.